CU Boulder. He then worked at many prestigious places, including the Princeton Plasma Physics Lab, Sandia National Labs. He has actually also been involved with our university on a number of collaborative research projects. And presently he's at Zap Energy based in Seattle and will deliver, I think, a very interesting talk today. He has said he's open to questions during the talk. So either raise your hand and type in the chat. We'll try to coordinate those as we go along. So without further ado, please take it away, Peter.
Awesome. Thanks, Mark. And, you know, I would have gotten my PhD at CU Denver if there'd been like this awesome plasma program back then, like there is now. So, yeah. Yeah, I went to the wrong CU at the one up in Boulder. Yeah, anyway, yes, I'm Peter Stoltz. I work at a company called Zap Energy. Zap is based in Seattle, but I work at the Denver office. If I could turn my computer around and show you outside, I can see Lakeside Amusement Park. So if you know where Lakeside is, that's where the Zap Denver office is. Yeah, and we'll talk today about commercial fusion energy. You know, if you know anything about it, this industry is just going crazy these days. So we'll talk all about it. Whoops, let's see. How do I go? There we go. Yeah, I just kind of looked online at my news feed and grabbed, you know, I don't know, 10 or 12 kind of images and articles there. CNBC, the New Yorker, the New York Times, Scientific American. There are articles everywhere about fusion energy these days. So it is a really popular topic. If you look in the lower right here.
I don't see your shared screen yet.
Oh, is that true? Do you see it, Mark?
The rest of us do.
I do see it, yeah.
Okay, great. Yeah, because it says I'm sharing. Yeah, so as long as everybody sees
Just ignore me.
I will, yeah. Yeah, and if you look in the lower right corner, and if you're a fan of American baseball, that's Alex Rodriguez, famous baseball player. He invested in fusion energy, and we'll talk about a few more kind of like famous folks and celebrities that are involved in fusion energy as well. Yeah, so fusion is a big deal these days. I probably don't need to tell you all this, but so here's a plot of why we need fusion energy. What I'm plotting on this graph here, this is greenhouse gas emission on the y-axis and years on the x-axis, and we're right around here somewhere. And you know, I think we all know what kinds of problems this is causing us right now. You know, we're looking at 2 to 3 degrees centigrade temperature rise if we don't do something drastic soon. So yeah, fossil fuels are kind of part of the problem, and we need a better solution for power going forward. Yeah. So here's kind of, you know, I put together a slide here of kind of what does the energy landscape look like right now. And on the left is kind of traditional fossil fuels. There's gas and coal and those things. And obviously I'm listing the problems at the bottom here. The problem with this one is emissions, of course. So that's that one. In the middle are renewables like solar and wind, which are great. And, you know, I'm a big fan, and I hope they are part of the energy solution in the future. I know they will be, in fact, but they still have some problems. They're not perfect. They're intermittent. It's only when the wind is blowing or the sun is out that you get energy. You need to somehow store that energy if there's going to be that intermittency. So storage becomes a problem. you need to get the energy from where you generate it to the grid. So, if you've ever driven out in eastern Colorado or up in Wyoming, you see these wind farms everywhere, but how then to get that energy from there to the cities? So you have that problem. And they're big, right? I mean, you need massive wind and solar farms. So they're low energy density is what I wrote down there at the bottom. You need huge wind farms and solar farms to make just a little bit of energy. And over here on the right is traditional nuclear energy. So this is fission energy. I guess if you're young enough, you may not even remember nuclear fission. It's almost gone these days. Some countries still use it. The US used to use it a lot, but it's got some serious problems. There is long-lived waste. So nuclear fission uses kind of heavy elements that tend to be radioactive for a long time. So you have to find something to do with these byproducts. That's a huge problem. They can be dangerous. I mentioned proliferation down there. It's kind of the same fuels that go into nuclear weapons. So they're just dangerous. They become targets for terrorism. So proliferation is a problem with nuclear fission. Reactor safety for the same reason. And there's just a social perception. If you remember Chernobyl, if you're old enough to remember Chernobyl, if you remember 3 Mile Island, there's just been some, I guess Fukushima, I forgot about Fukushima. There's been some just terrible disasters at these kind of nuclear fission plants. So there's a social problem there too. Okay, so that's kind of the traditional landscape. Who's coming to save the day? Well, fusion, I hope, is coming to save the day. So fusion is really kind of the perfect energy source. It really is. It's kind of the ultimate energy. It's one way to think of it is like a star in a bottle or a star in your lab or your garage. Of the problems we listed on the previous page, fusion doesn't have any of them. It's clean. Instead of using these heavy elements that end up being radioactive for a long time, fusion doesn't do that. Fusion uses light elements with no waste byproducts. There's no greenhouse gas emission, so it's not like traditional fossil fuels. So it's a clean energy source. It's safe in a way that nuclear fission is not. These, energy based on fusion can't have these meltdowns and these runaways. There's a little bit of radioactivity, and we'll talk about that, but it's very limited. So we'll talk a little more about that. And it's on demand. So if you need fusion somewhere that you can't get energy to, you just go there, you build your fusion plant there. It takes minimal fuel. When I talk about my company's project in a little bit, we use milligrams of fuel. So just tiny amounts of fuel. And you can power your fusion power plant. Okay, so I just listed all the good things. So why are we not doing it? Mark, why are we not doing it?
It's very hard. People
It's
have been
hard.
trying to do it for 50 years.
Yes, that is the correct answer. Yeah, that's right. It is, the promise is there, all these great things. And the reason we're not doing it is really hard to make a nuclear fusion power generator. We've been trying forever. I mean, the sun, that works. It's, if we have kind of the sun's mass and scale, we can do it. The sun is also really hot, millions of degrees Celsius. So yeah, you'll hear kind of that temperature benchmark a lot. We need to find a way to make things that are a million degrees Celsius. And, you know, when you think about things being that hot, you start wondering, well, what can hold them, right? If something's that hot, whatever you put in contact with it is just going to melt. So, you know, these are the problems that we're facing. Yeah. And yeah, I don't know how deep we're going to get into the science. I put a little picture over here. Can you see my mouse, Mark? Works okay if I just mouse point?
Yeah, we can see it.
Okay, yep. So I put a little picture here of kind of the most common fusion fuel cycle for these kind of commercial fusion generators. It's got a hydrogen 2 and a hydrogen 3. So this one you'll hear called deuterium a lot, and this one you'll hear called tritium a lot. So they're really just protons, right? The red things are protons. And the gray things are neutrons. So they're kind of isotopes of hydrogen, basically. Yeah, and what you're trying to do, of course, is you put them together. And it turns out when you do that, they kind of want to, sort of, and they will eventually form a helium. So they just come together, form a helium, and release energy in the process. Yeah, so, right, okay, on we go. So, yeah, okay, so fusion is really hard for the reasons of it being hot, it being hard to do. And so here is a picture. I want to talk about two of the biggest efforts to make controlled fusion. So here's one of them. It's called ITER. That's an acronym for International Thermonuclear Energy Reactor, Experimental Reactor. I forget the exact acronym. Everyone just calls it ITER these days. It's an international collaboration. It's being built in France. It's currently under construction today, right now, as we speak. There's actually online cameras where you can watch the construction of ITER. It is going to cost $50 billion to build one machine. One. That seems crazy. Also, this is a picture of it. Those are people. ITER is gigantic. So I have a couple problems with ITER. I'll show one more picture of it here. There's a picture of it. You know, I hope it works. I'm not anti-ITER by any means, but it costs $50 billion. And that's just to make one. Like if something goes wrong, what are you going to do? Build another one for another $50 billion? Like, I don't know. It doesn't make a ton of sense to me. Also, it's taking a really long time. You know, it's not planning to be operational for years to come. But when I showed you that plot of greenhouse gas emissions, like we kind of need to fix this problem today. Yeah, now, so that's ITER. I'll talk about one other kind of government funded project. You know, ITER is not a private fusion endeavor. It's a public government funded endeavor. And here's another one, a really famous one here in the US. It's called the National Ignition Facility. So NIF is the acronym. It's in California. It's just run by the US. And NIF is very successful at making fusion. In fact, they did something incredible. They have achieved something no one else ever has achieved. I'll talk about that in just a minute. But the problem with NIF is that it also costs billions of dollars, and it's also gigantic. Like again, here is part of NIF, and those are people. Like, you know, NIF is huge, and it costs a lot of money. So it's another example of kind of a government-funded effort that is maybe just not nimble enough for kind of solving today's problems. But NIF did do something amazing that I'll tell you all about. You know, have you ever been like out camping and you make a campfire, right? And you can light it with a match and it kind of burns until like the kindling and the paper is gone, and then it goes out, right? And then you can light it again with a match and it'll do the same thing. And like every fusion experiment to date is like that. Like we can make them work for a second, but then they go away. Now NIF is the only machine ever that has achieved what we call ignition, right? So they got this thing to actually burn. They turned it on, they got their fusion going, and it actually caught fire and kind of actually started burning. It was an amazing achievement. It made it into the New York Times down here. And so that was great. So kudos to NIF. And again, I hope NIF is super successful. Every other fusion experiment that I talk about today has yet to achieve ignition, but we're working on it. Okay, so so those are two government-funded projects, this ITER project and this NIF project. And you know, my claim is that they're just too big and too expensive to really work for today. So what's happened in the last few years is there have been just a ton of people that have said, let's try to make it smaller and faster to create fusion. And so companies have started spinning up. Like people don't want to wait around for the government to solve the problem. And so there started to be little companies all over the globe. People are trying to build their own fusion reactors. So yeah, I thought I'd talk about this plot for a little bit. This graph right here is probably my favorite. This one here, where it just shows you that in the previous 20 years, people invested about $2 billion in fusion. And then I looked up, and this is actually an underestimate, but I looked up in just the last 3 months, there's been $2.4 billion invested in fusion by private enterprise. So it's really kind of, it's an amazing boom time in fusion energy startups. This list here is a list of some of the folks that are investing in this. Chevron, so the oil companies are getting involved, which is interesting. Chevron is actually a main funder of Zap Energy, the company I work for. Google is getting involved. Google has money in this now. Breakthrough Energy Ventures is Bill Gates' kind of venture fund. So Breakthrough Energy Ventures is Bill Gates. You see Jeff Bezos' name there. There are a lot of big players in this world right now. And they're kind of spread all over the globe. So here's in the lower right here is a picture of kind of where these companies are. There's a lot in the US, 13 of them. Yeah, I'll show you in a minute. One of them's in Colorado, actually. There's some in the UK, some in Europe. Yeah. And as you can see in kind of the upper right here, there used to be one company, two companies, and now there's, over 20. So yeah, it's really growing. All right. Whoop. Let's see if, yeah. All right. So I just put together a little list of kind of some of the bigger name companies around the country, around the world. And I'll talk about a few of them. Right here in the kind of upper right, that's Zap Energy, that's us, that's my company. Commonwealth Fusion Systems, I'm going to talk kind of in detail about them. They're in Boston. People are really excited about CFS for reasons I'll explain. Helion is in Seattle, just like Zap Energy. They just raised $2 billion this summer, $2 billion for their company. Horn Technologies, this one here, this one's in Colorado. It's in Longmont. If you ever want to stop by and visit a fusion company. This one down here in the kind of lower left is TAE. They used to be called Tri-Alpha Energy, but they just go by TAE these days. We're going to talk in detail about this one as well. Yeah, so that's just kind of just trying to show you just, you know, there are many people trying to pursue this fusion energy dream right now. Yeah, okay, I think that's all for that one. I put up a picture of just kind of different ideas that these companies are pursuing for kind of how to hold this just incredibly hot, like I said, millions of degrees Celsius object that we need to power our generator. And so people have come up with all kinds of ideas for this. This one up here is called the tokamak. This is the one that they're pursuing at that giant international facility in France. That's the tokamak. It's just a donut, right? A lot of these are kind of similar shaped. This one's kind of like a more like a line. We'll talk about that one. That's that company TAE that I told you about. So we'll talk more about that one. This one down here is very interesting because you remember I was complaining about ITER that it was too big, but this is this company in Boston called CFS, Commonwealth Fusion Systems. They have figured out a way to really minimize this thing. It's super interesting, super clever, and people are really excited. So we'll talk about that one. Yeah, so that's just kind of, I just thought I'd show you all pictures of all these different ideas that people are coming up with for kind of shapes of ways to hold these hot objects that we need at the center of our generators. All right, so the first company I was going to tell you all about is this one called Commonwealth Fusion Systems in Boston. That's an artist rendering, by the way. It's not really that nice there. But yeah, that is a company in Boston. They've become one of the bigger companies around. They've got about 200 employees these days. Just this summer, they announced over $1 billion of investment. Bill Gates is one of their main investors. So yeah, I think this is one of the companies that people are most excited about. And, you know, what are they doing? Why, right? Let's talk about what they did. How do I do that? Yeah, okay, right. So earlier on, that giant machine in France I showed you with the picture of all the people standing inside the tokamak. Commonwealth Fusion Systems is building a small one, a mini tokamak. It's only 2 meters tall, right? So if I put, you know, people on here, it would be about, the person would be about that big. So that's great. These things are much more compact, much easier to construct. And CFS is already constructing one, and they're going to have it operational in just a few years. The technology that they use, the kind of breakthrough that allowed them to build this thing much smaller is really interesting. So I put a slide about that. What enabled them to do what they need to do is a brand new flexible high temperature superconductor. So they need these superconductors to kind of create the magnetic fields that they need to contain their hot plasmas. And those magnetic fields, it's always been really hard to generate them. But someone came up with a way to make, it's essentially tape. I mean, you can almost tell that this is like it's like ribbons, right? And you can make now superconductors. If you don't know what superconductors are, they're essentially materials with no resistance. You can flow electrical current through them without losing any energy to heat. So it's an incredible breakthrough. They've they've come up with a way to make this high temperature superconductor in literally it's like masking tape, and they can just wind it. So it's flexible, it's not brittle, it's not like ceramic, like high temperature superconductors used to be. So it's really a material science breakthrough that Commonwealth Fusion System is using to enable their device. So it's really exciting. I think they're going to have a lot of success. Here's a picture of what they hope their final design looks like, and it has people on it. So you can kind of see what the scale is. So, you know, yeah, it's a very compact, small device. And you know, what's funny about it is that, you know, with all the people in France working on that giant international collaboration, I think this little company in Boston is going to beat them to having a plasma in their device. Yeah, so just kind of because it's so much smaller and because they're just working so much harder, I think they're going to, you know, CFS is going to have a working tokamak before ITER does. All right. Okay, so this is company number 2. This one's in Los Angeles. It's called Tri-Alpha Energy. It's called TAE now. They just go by their acronym. There's a picture of it. It's in Los Angeles. It's got a few hundred employees also. And again, they've raised just incredible amounts of money lately. Again, over $1 billion. This company has actually been around for a long time. Founded in 1998, so really one of the very first fusion startups. And Harry Hamlin is one of their main investors. If you don't know Harry Hamlin, he was in a show called LA Law on TV in the 80s, and then he was on Mad Men, if anybody watched Mad Men. So he's a very famous actor, but also kind of a amateur scientist on the side. He considers himself an amateur scientist. So yeah, he actually was one of the first investors in TAE. And Google also is heavily invested in TAE. So TAE has a lot of interesting backers. We'll talk more about their device. They're standing right in front of it there. This is their fusion machine back here. Yeah, so the one that they're using is more of a line and less of a donut. So they're using a linear type machine. The reason they do that is because it just requires a lot less material, a lot less magnets that are very expensive. Yeah, so I guess that's a theme. I didn't even realize that till just now, but you know, the Boston company, Commonwealth Fusion, like their breakthrough was that high temperature superconductor that let them make magnets more cheaply. And TAE, their kind of breakthrough is that they built a machine that doesn't require as many magnets. So so there's a theme there. So yeah, they've got this device that's already operating, in fact. And one thing that's interesting about them is that they plan to use a very novel fuel inside. Yeah, they're going to, in fact, it's why the name of their company originally was Tri-Alpha Energy, because they planned a kind of fuel process that would make 3 heliums. If you're not kind of familiar with the kind of atomic or nuclear physics world, you know, a helium is often called an alpha particle. So yeah, they plan to use this very novel fuel that uses boron and helium mixed together to make 3 heliums. Mark, any idea why that's a better fuel cycle?
With 3 heliums versus the hydrogen.
Yeah, right. Versus the deuterium tritium one.
Well, if I'm reading off your slide,
Yep, you can go ahead and read, yeah. It does it right.
Is it the no neutrons? Or?
Yep, it is, yeah, that's right. Here,
Okay, so if I could ask you actually a question about that, since you're putting me on the spot. Yeah, this diagram, right, you have the energy and the neutron going off, right? I was under the understanding that part of the energy released is in the neutron. And, you know, when that hits the walls, that's where you generate heat, right? Or is it,
yeah.
or is it also, is there like, you know, maybe you could talk about the other form of that energy and how it's captured.
Absolutely. I've got a bunch of slides on that coming up.
Okay.
So yeah, sorry, but yeah, I will get to that. Yeah, so I'll just mention, I'll mention it briefly here because Tri-Alpha is using this extremely novel fuel concept. So, you know, this is the traditional fuel concept, right? And you put these two hydrogen isotopes together, and off comes a neutron with a lot of energy. Off comes this helium or alpha particle with a lot of energy. Turns out neutrons aren't the greatest. Like, turns out that they are hard to capture because they don't have any charge. They can hit the metal in your device, in your building even, and weaken it. Like they're moving fast, and if they hit your you know, the structure of your building, they can knock things out of place in your, you know, girder, your iron girders that are holding up your building. And so neutron damage is a real thing. And so people don't love neutrons in their fuel reactants. A lot of times you just have to live with it. But Tri-Alpha Energy, so this company that we were just talking about in Los Angeles, these guys, right? They've got this idea to skip that. They're going to use a totally different fuel, won't have any of the neutrons. Everything that comes out is going to be helium, much easier, much better fuel cycle. Why isn't everybody doing that, Mark?
No idea.
This fuel cycle takes a much hotter plasma, much hotter. So you've got to be able to make your instead of just millions of degrees Celsius, it's now tens of millions of degrees Celsius to run this fuel in your machine. So it's a lot harder. I mean, they've got a huge challenge ahead of them. But if they can do it, they do have this much better fuel cycle. So it's exciting. They're a really exciting company. I applied for a job with them and they did not offer me the job. I don't know what that says, but oh yeah, look, I have a slide about that. So they used to hold the record, in fact, for the hottest contained plasma. Among all of these fusion startups, right? TAE had the record for a long time of the hottest plasma. Just recently, I mean, like literally a month ago, this UK company that I'm not going to talk about, but there's a UK company called Tokamak Energy that did actually break the record. So they're up to 100 million degrees Celsius in that one. Yeah, but for a long time, I mean, this is TAE's whole game, is to create incredibly hot plasmas. So yeah. Yeah, so there's a lot of reasons to be excited about TAE. All right, one more company to talk about, and then we'll just kind of get into some other stuff. But yeah, one in Boston, that was the Commonwealth Fusion Systems with the cool tape. TAE in Los Angeles, and one in Seattle. Zap Energy, so kind of a newcomer, only around for 3 years now. Zap Energy started in 2019. Right now, today, we are at about 100 employees, not quite. And our latest round of funding raised $162 million. So a lot of investors are really excited. The big investors in Zap Energy, like I said, Chevron, Bill Gates now is an investor. I mean, we're kind of neighbors, right? With Bill Gates, we're right there in Seattle. So yeah, kind of, he should support us, right? And so, So Zap Energy has yet another idea about how to make a much more compact fusion plasma. So I'll talk a little more about that. But that on the left here, this is Brian Nelson. This is our CEO, Benj Conway, and this is Yuri Shumlak on the right. Yuri and Brian were professors at the University of Washington for a long time. Benj is kind of a business startup kind of guy. But yeah, yeah, it's a spinoff out of the University of Washington. Looking at the background photo, that picture might be from the University of Washington. Here's a little kind of description of how this device works. Here's a picture of it over here. Kind of a large scale picture. This whole thing is, yeah, maybe 2 meters. So, you know, tabletop-ish, about the size of a person, top to bottom. Yeah. These things up here, these black cables up here are gas injectors. This kind of light gray stuff, you can see it better down here because it's kind of glowing. This light gray stuff down here is lead with lithium in it. This is how we absorb the neutrons in our machine. This is our heat transfer mechanism. Actually, my very last slide that I'm going to show, I bring up heat transfer. So think about that. If you're an engineer that's interested in heat transfer, I encourage you to think about this problem of liquid metals because it's a big one. So yeah, this light gray area here is all liquid lithium. Yeah, and so now that's kind of just like a description of the device. Now over here, I'll show you kind of on the left, I'll show you like the whole cycle as we imagine it. So these fuel injectors up at the top will inject the deuterium and tritium gas. So way back at the beginning, I showed you that picture of the colliding deuteriums and tritiums that's going to produce a neutron and an alpha particle. So we inject that way up here. We apply a really high voltage between this thing in the middle and this thing on the edge. So it's like a coax cable, basically. I mean, not like a coax cable, it is a coax cable. It's maybe a 5 or 10 centimeter gap between the inside and the outside. And it's, you know, like I say, it's a coax cable. We're going to apply a big voltage across that to kind of cause a spark in that deuterium and tritium gas. So that's this picture, is we've got that spark. The kind of self-magnetic force on that spark causes it to shoot forward down the coax. If you've ever thought about a rail gun, exact same process. So the Navy uses this to kind of shoot projectiles into the air. We're using it to shoot deuterium and tritium forward. And then we just have this chamber where we catch it, and that's this third picture right here. So we catch all of our gas after we've accelerated it with this kind of high voltage. It smashes together in this little chamber. Neutrons go flying out, alpha particles go flying out, and that's this last picture here. So we absorb all of that energy in this liquid metal blanket. That's this gray part. And so we have hot liquid metal now, and these little holes here, this is where we're going to pump that hot lithium out and use it to turn a turbine, boil water, you know, just turn a traditional, just like regular old energy generators work. We're just going to boil water, use the steam to turn a turbine. So yeah, we're going to use kind of the thermal processes that we've now got. We've got a hot metal that we can use to transport our energy. Yeah, so that's kind of the Zap Energy concept. It's compact. It's like I say, it's only a few meters long. That's a little bit cheap. And this is another thing I want to talk about with you all. When I get to the end of my talk, I'm going to try to convince all of you to come work on fusion energy. So that's another thing I wanted to talk about is this part is compact. But Mark, what am I not showing in this picture?
The rest of the turbines and all that? Or?
Well, that too, actually, that's a good point. I'm not showing the power supplies. I just told you I needed, a huge voltage here. So I'm cheating a little bit because I'm not showing the power supplies are massive, way bigger than this machine. And so it's a little bit of a cheat. If we can reduce the size of our power banks, that will really help us. And so at the end, I'm going to talk some more about that.
What's the voltage level that you apply there?
Yeah, I might even say it here in a minute. Here we go, right here on this slide, Mark. Hey, there's an actual picture. This picture was in the New York Times. That was a very exciting day for us at Zap Energy. We made it into the New York Times. That's Morgan Quinley right there. That is one sharp guy, man. I'll tell you what. Working at Zap Energy is worth it just so you can talk about physics and science and engineering with Morgan. Yeah, so here's a picture of our device. Like I said, the device itself is really kind of person size, tabletop size, right? Oh, here, this might help. This thing right here, when we have it in the lab, it's sideways, right? It's that. So this part right here is turned horizontal in that picture. That's this thing right here, right? We don't have in the lab right now. We don't have this container, the liquid metal container. So right now in the lab, it just looks like that, and we orient it this way just for ease. Yeah, so okay, here's some answers to your questions. I mean, these are incredible numbers, really incredible numbers. A mega amp of current that we want to flow in this device, tens of kilovolts. We've gone up to 25. We don't want to go up to 25. Less voltage is better because it consumes less power. But yeah, tens of kilovolts is the answer to your question, Mark. Hundreds of kiloamps and even a mega amp of current. And tens of millions of degrees Celsius in this thing. So we call this machine that we're building right now, we call it Fuse Q. Fuse stands for Fusion Z-pinch Experiment. It's called a Z-pinch because when you look at it from this point of view, if you're thinking about cylindrical coordinates, right? This would be the Z-axis in cylindrical coordinates. So that's why we call it a Z-pinch. Yeah, so it's called a fusion Z-pinch experiment, and we put the letter Q at the end. One of the kind of metrics that all fusion companies are working towards is energy out versus energy in. So like this machine works right now today and produces neutrons. So it's working, but it takes more energy in than it puts out. So it's not a very good power plant yet. But Q is that measure. So you'll hear this a lot if you talk to fusion energy scientists or engineers. Q is the measure of energy out to energy in. We want it to be bigger than 1. We want more out than in. And so that's why we put the letter Q after it, because we're trying to emphasize that we're going to get more energy out than in.
So
Um,
Peter, when you say first plasma any day now, that means a Q greater than 1, or I guess you said you already
Great
have
question.
fusion
Yeah,
going on in there.
we have a mini version of this machine already operating.
I see.
We purchased it from University of Washington. We literally like got a truck and moved it from the University of Washington campus to our lab. So we have a mini version that runs right now. This machine that we are building, our first machine at Zap, is it's actually running. When I say first plasma will be any day, there's actually already plasma in it. So so yeah, it should be working anytime. Yep. All right. Oh yeah, let's see. What did I want to say about this? A couple things. I mean, the scale of what we are imagining is very modest and modular, right? So you could imagine having one of these in your garage or outside your house, right? It's really a modest sized machine. The energy that we're hoping to get out is 50 megawatts. The power, I should say, that we're hoping to get out is about 50 megawatts. So, you know, what's that? Maybe power like a little neighborhood or something. So you know, you can imagine building up a gigawatt style power plant out of these little modules. Yeah, sorry, there's a lot of words on this page. But yeah, just what are the takeaways? Kind of the size and the, you know, that we're hoping to get about 50 megawatts out of this thing. Okay, so yeah, this is one thing I wanted to talk about today, because I figure a lot of you on the line here are about to get your degrees and you're about to come out into the world and look for jobs. And I want to encourage you to look at fusion as a career. And I know what you're thinking. You're thinking, well, I don't know much about plasmas. Plasmas seem weird to me. I took Professor Golkowski's course and didn't understand a thing. I know, right, that you're thinking all those things. And I'll tell you a couple things. Number one, I still don't understand plasmas. And I've been doing this since like 1990 something. So yeah, no one understands plasmas. Mark, would you claim you understand plasmas?
No, despite my best efforts, I do not.
That's right. So don't worry about that part. And second of all, I want to make the case that we need every kind of engineer to help work on fusion, every kind. So the first one I listed is people that just understand thermal engineering, people that just understand heat transfer. Forget the plasma, right? The plasma, it's just there to make the blanket around it hot. And then we're going to use that hot blanket to drive our turbine. We need to understand that. We need to understand, you know, how we're going to transfer that heat. So maybe you're a thermal engineer and you're interested in kind of complex fluids. Like I say, we've got a liquid lithium shell around our machine. Liquid lithium. It's a really novel kind of complex fluid. It's got a lot of interesting kind of thermal transfer properties. And so if you're interested in that kind of thing, come work for the fusion industry. Everyone's using liquid lithium, by the way. I guess except maybe TAE, they don't need it. But almost everyone is using a lithium blanket. So yeah. Electrical engineers, holy moly. Again, forget all about the plasma physics. We need to drive tens of kilovolts and hundreds of kiloamps, if not a mega amp. Just designing that circuit is hard. You know, it's easy to draw like RLC circuits on a piece of paper, but when you go to make them, the properties involved of making a real circuit that can handle that kind of kilovolts, that kind of amps is hard. I'll give you an example. Switches, right? Imagine that we need to charge up our battery bank up to 10 kilovolts, 15 kilovolts even, right? And then we're going to discharge it into our plasma. But in the meantime, we need to hold off that 15 kilovolts. We need a switch that can stop 15 kilovolts from flowing without breaking down, right? That is a powerful switch. We worry about that a lot. Just the switching is a really hard problem. So we need electrical engineers, just straight up people that want to work on circuits, high power circuits. And it's not just that, like every fusion company is going to need that. Maybe you're a mechanical engineer. We have all kinds of mechanical engineering problems in this field, especially vacuum science, right? Especially vacuum science. We're trying to contain this device inside of a vacuum. And so if you are interested in vacuum engineering, I encourage you to come work in fusion. Material science, we have all kinds of material science problems. Again, if you're interested in material science and you're a mechanical engineer, lots of jobs in fusion. And this last one is really interesting. Maybe you just like fluid flow. Maybe you just like the fluid mechanics, right? Where'd my picture go? Yeah. You know, if you talk to the scientists at Zap, so that's me, right? I'm a scientist. We're interested in kind of this part. We're interested in the kind of ionized gas, plasma. That's the fascinating part. If you talk to the engineers, if you talk to the people really building this thing, they are worried about the gas valves. That's their number one thing. They say, look, if this thing's going to work, we need these gas valves to work and work right. You have to time things to get a perfect little donut up here. We need all 4 of our gas valves to fire at the same time and the same way. They need to be reliable and repeatable. So if you ask Morgan, he's going to tell you the gas valves are the #1 problem. You don't need to understand anything about plasma physics to do that. You just need to understand fluid mechanics. So we hire people to work just on gas valves. We also hire technical project managers. If you're just kind of interested in the overall picture and helping engineers stay on track and do things, that's another area that we hire people all the time. So that's kind of the end of my talk. I actually have some more that we could talk about, but I'll stop, Mark, and maybe we could do some questions. And if there's still time, I'll show some more fun slides at the end.
Sure. No, thank you very much, Peter, and thank you for the slide about the career opportunities. I think
Yeah. No, I mean, like, look, if you open up the TAE website, if you want to live in Los Angeles, I mean, they've got hundreds of jobs posted. CFS in Boston has hundreds of jobs posted. You know, we've got dozens of jobs posted. So there are jobs everywhere right now in fusion energy.
Okay. So questions from the audience. Any? Sure. I don't think there's anything in the. Okay, I think there's at least one in the chat. Okay, the liquid lithium. Maybe you could talk more about that. There's a question here. Does it basically have a lifespan like a battery, right? That a battery, you know, you charge, decharge, it's basically its performance decreases. I assume here you're using it as just a heat transfer fluid. So maybe it's much more chemically simple.
I think you're right.
And why is why liquid lithium? Why not other materials? Is it
That's a-
because it can, maybe you can speak about that.
Such a great question. Yeah. So first of all, you were totally right. I'd actually never thought about it, so it's a great question. But I think there are no like battery lifetime material issues with the liquid lithium blanket. It's the reason we use lithium. It's a little complicated. The reason we use lithium is because where's my fusion picture? That one. Part of our fuel is this funny hydrogen isotope called tritium. This one over here, deuterium, turns out there's actually quite a bit of deuterium around on the Earth. Just kind of hydrogen with one neutron attached to it, right? Turns out you can find that pretty much anywhere. It's in seawater everywhere. So no problem there. This one is tricky. So that's a hydrogen with two neutrons on it. There is a way to make that using neutrons and lithium. So we put lithium in our blanket on purpose. Where's our blanket? Right there. Go back. Yeah, we put lithium in our blanket on purpose because we're breeding our own fuel to use in our reactors. So we need a way to make tritium, and that's why the lithium's in there. It's mostly molten lead, I should mention, right? It's mostly molten lead with lithium embedded in it, right? It's a flibe of some kind, right? So yeah, it's lead to stop the neutrons and lithium to kind of breed this tritium. But yeah, so it's a liquid lead metal that we've got lithium inside. Yeah, great question though. Kind of a complicated answer, but I hope it made sense.
No, great, thanks.
Yep.
All right, thanks. Any additional questions? Again, you can write them in the chat. You can just unmute and speak up, whatever works. I guess we got one. Somebody just unmuted. Go ahead.
So my question is almost like in how much cost the unit that's produced like in the 50 million watts, or how much the kilowatts cost for one unit from the one unit?
Yeah, I don't actually know that number. So let's see where, yeah, I put it here. Right. So this kind of scale device, like how much would it cost in production? I mean, I know how much the research device costs. This one that we're building right here, I probably can't give away that number. That's probably a proprietary secret. But when we turn it into a little power generator like this, how much are we imagining it would cost? That is a great question, and I don't know the answer. Yeah, I guess I don't know.
Could you maybe, Peter, follow up on that? Let's say you have this one that you have in the picture, right? How much fuel would that need if it's operating at the 50 megawatts?
Yep, that's a really good question. I mean, I may not know the exact answer to that one either, but when we do this kind of level, mega amp current, 15 kilovolt shot, we put milligrams of fuel in there. And so when we try to turn it up to the 50 megawatt level, maybe it'll be a little higher than that. Maybe it's 10 milligrams of fuel, but it still won't be too much. And the fuel is, is that deuterium and tritium. It's the heavy hydrogen based.
And so you would need a tank of that like on the side, right?
100%.
Okay.
100%. Yep. You don't see it in the picture there, but there's definitely tanks of deuterium just sitting in the lab there. Absolutely. We've never fired tritium that I know of. Pretty sure we have never fired tritium because it's crazy expensive. It's really hard to get. So we just use pure deuterium. It almost works the same. Yeah. Yeah, sorry, I don't actually know the kind of answer to the cost question.
And that, again, going back to that conceptual drawing you had, right? Is that, does you get electricity right out of that thing? Because I'm wondering, is the water, the steam turbines they're all included in that? Or?
Yeah. We hire people that design power plants to work at Zap, and I have not talked to them. So whether that's actually included inside our little shell case there, that's a good question. I mean, I guess it would have to be. Let's say yes, Mark.
Mm-hmm.
Yeah.
And I'll ask one more. So you had this very interesting kind of theme in your talk about the size, going from the giant government projects to the smaller ones. I think there's a lot of issues that go into that. I remember in one of Richard Feynman's books where he was talking about this kind of research back in the early days, comparing the different universities, and it turned out the smallest one, I don't remember if it was now Cornell or Princeton, right, where they had like the lowest funded reactor, but they got the best results because it was small, so they could keep rearranging it, and
absolutely
it was like on a tabletop as opposed to filling the whole room. So there's definitely a kind of iteration of innovation.
Absolutely. Like I look at this thing, like this is ITER, right?
Yeah, you want to change
it. What if they're like, whoops?
You need to put out a bid, right, to a subcontractor.
What if they're like, whoops, this should be, a little bit bigger? Well, what are you gonna do? Like,
yeah, but at the same time, the French, despite the work ethic joke you made during your talk that I caught, the size is because you're trying to get to the scale, like you said, closer to what the sun is, where you have less instabilities, less issues, right? So. If you have any additional kind of comments on that, right? There is something that motivated the ITER people to go to that.
100%. Look, I trashed ITER. It's easy to trash this project because it is so big and expensive. But I'll tell you what, it's going to work. Absolutely, it's going to work, right? None of the companies that I mentioned, Commonwealth Fusion Systems, Tri-Alpha Energy, Zap, none of those are guaranteed to work. Those are ventures, right? Those are speculative. ITER is going to work. Like the science is proven. So that's what ITER has going for it. It's a sure thing. So,
maybe I can add to this, Peter and Mark. This is Akash. So, I think ITER is very much based upon a device which achieved breakthrough. It's called the MAST, right? The mega ampere spherical tokamak.
Yep.
Right, in Britain.
Yep.
And I think they've used the same exact form factors, but just made the design bigger. And the other thing that is going for ITER, it's an international project. I think it includes India, Japan, South Korea, Europe, US, and one other big nation. I'm not sure, Canada maybe. So you're absolutely right. There are several components that people still don't know what is going to happen to them, like the diverters that are at the bottom, right? But yeah, as you rightly said, the scale basically is of a real power plant, right? It's not going to be these short pulses of microseconds producing gigawatts, and then hoping that somehow you fill up the other 10,000 microseconds there, right?
Yeah, that's right. ITER has a lot going for it, for real, and it's going to work. So that's the main thing it has going for it. Yep.
Oh, very, very nice. And thank you, Akash, for that info. And then one more, you kind of showed a map of world map of countries interested. And you kind of showed the recent funding, right, which is really spiked, but I assume it's all private sector funding. Mostly, right? Do you think, even though the government now seems to be kind of ramping up in terms of research funding, right? There's all these bills being passed that really want to close the gaps and ensure the US is at the forefront of technologies. What kind of comes to mind is quantum computing, artificial intelligence, 5G. Fusion, unless I've missed it, maybe you can correct me wrong, does not seem to be at that level. Is it the government's kind of pulled back from this, or is it that is it because they see it as too risky, or is it that they see it as mature enough where they don't need to support it anymore? These companies have sort of picked it up.
that is a really interesting question, right? Which one of those two is it? So there is an arm of the federal government called ARPA, Advanced Research Projects Administration. The defense one is called DARPA, that maybe some of you have heard of. The energy one is called ARPA-E. And so ARPA-E does invest heavily still in fusion and in these companies. Zap Energy got a lot of ARPA-E money to get going at the beginning. So that there is some, but you're right, it's not a crazily heavily funded federal effort by any means. Yeah, but why exactly? That was a great question. Yeah. Who can we call? Diana DeGette, I guess.
Great. Any last few minutes? Any other questions from anyone else?
I have a couple of questions.
Yeah, go ahead.
It's almost like one question, but it's kind of a two-parter. So, I guess one with like Zap specifically, right? One of the maybe things that want to be like resolved more in the future has to do with like the power supplies, right? Because I remember,
Yeah.
yeah, it was mentioned that they're really big and stuff, and I'm not sure, but I'm assuming some of the maybe like inefficiencies come from the fact that there's a lot of energy wasted throughout the process. So like I'm guessing like the energy transfer is nowhere near 100%
Absolutely.
or something.
Yep.
Okay.
Yep.
Uh,
I tried to find a picture with the capacitor banks in the back, but you know, the capacitor banks are room sized. They're giant, and we charge them all up and then, you know, discharge them into our little Z-bench machine. Yeah, so it's a lot of energy that we're working with to store.
Okay, yeah, and so I guess that kind of leads into the main question I wanted to ask, which is that I don't know if this is kind of like on the same track, because I only know about this technology in like the sense of like phones and computers and stuff like that. But I know that there's like been, I guess like I've been hearing things about like gallium nitride or whatever, and like things that like, yeah, and things that like really seem to like reduce the size of power supply or like chargers and stuff like that. And I was like, I don't know if that like same kind of technology is applicable to the kind of things that you were doing, and like if you guys have thought about that.
Well, so I'll give you two answers to that. The first answer is I don't honestly know. But the second answer is that, you know, novel material solutions, like, you know, new materials that would present kind of higher density energy storage, better capacitor banks. Oh my gosh, yes, right? Sign us up for that. They have to be fast, like they have to discharge fast. Microseconds of discharge time. So yeah, that might be one issue, right? Is that these novel materials might be kind of slow to discharge on our timescales. Yeah. But yeah, no, I love it. I love the idea of kind of reducing the size of the power supplies through novel material innovation. Yep.
Okay, great. Any last chance for questions? So Peter, what can you give us a prediction? If we were to meet a year from now, what any big things on the horizon that you see that we might expect, or maybe you being a billionaire with Zap, or is it?
Yes, I will own Lakeside by that time, Mark. I will own it. Yeah, I don't know if by next year, but I can tell you that if you read our website at Zap Energy, this machine right here is supposed to put out more energy and neutrons than electrical energy that it takes in. It is supposed to be a net energy generator in 2023. So next year, next calendar year.
Well, if that happens, you heard it here first. So
yeah, that's right.
So let's thank our speaker. Feel free to unmute and holler or cheer. or virtually clap. Very interesting and fascinating talk, Peter. So thank you once again.
No, thank you all.
Okay,
so much.
and for
Thank you.